Thank you for watching this extended version of the MONA program. What we're going to do now is to demonstrate the individual maps that we have created and to describe some of the features that is incorporated into the map. Here we have porosity and coating failure strength map, and we can see the porosity on this axis and the failure strength on this axis. This data is gathered from a standard C633 tensile adhesion bond test results from available literature. So we can see now the default version is, you can see the different materials, and this is highlighted by the different colors, and actually it also blinks on the screen here. The axis can be a linear scale or a log scale depending on the user preference. Now let's use a log scale and a linear scale for the x-axis. Now say if I do not want coating composition and I want to look at something else different, say coating material classes, which is we have separated to ceramics, composite and metals. We can see the distribution. Now say if I want to go to say thermal spray type, again we can see the APS, cold spray, D-gun and flame spray. This literature will be expanded on in future versions, and we have around 100 to 150 points plotted now. Now say if I want to look at the different failure modes, I could do that too. The white being it failed beyond the limits of the glue. The failure occurred at the glue, not on the coating. So we have the various three classes of failure: mode 1, mode 2 and the mode 3 mode that we have. Let's go back to failure strength. Again, this is a color intensity map. So thank you. This is one of the 7 maps that you are viewing now, and let's move on to the second one. Okay, now we see a coating hardness and porosity map for thermosprayed tungsten carbide cobalt coating. One of the features we would like to demonstrate that it's possible to change the axis to suit your preferred view. Say if you want to change the axis from hardness to porosity, we can do that for the y-axis, and the x-axis we want hardness instead, we can also do that. And we can also change again from a log scale to a linear scale, and all this is possible. Let's switch back to the original, because that is our preferred view, and linear. Okay, so now you can see the different composition by mouse overing. Tungsten carbide 12%, tungsten carbide 12%, 17%, M-dry 1983, and so on and so forth. And the various papers are in this legend box again. We can look at the different spray types: APS, cold spray, the D-gun, HVOF, and VPS. There are around 100 points in this map, and we are constantly increasing the data set pool. One of the trends that we can observe is higher the porosity, the lower the hardness. This is viewed across all sample set. We can also view different testing loads that is used in the Vickers hardness indent. 200 grams, 300 grams, and so on and so forth. We are able to plot this and see what's the typical load, which is 300 grams, being tested in the various research papers. Again, if I am interested in this point, I can click it. Mouse overing it allows me to see the X and Y axis values and also the paper. Thank you. Now we see a typical map of standoff distance versus particle size, powder particle size for thermal spray coatings. This is a rather new map that we have just created, and it probably has around 50 points only. We are still building on this database. It's created mainly to compare with the traditional thermal spray methods versus the suspension spray methods. As you can see that the particle size is all the way down to the nanometer range. Now we have the default setting of standoff distance versus particle size, one being the y-axis and the other being the x-axis. A linear versus log because of the different particle size that's been used. Now we can mouse over and see the different materials, YZ, alumina, hydroxyapatite, YZ again, and so on and so forth. Let's go to the different type of thermospray methods, which was the interest of this map. We can see the suspension plasma spray, the high velocity suspension oxy-fuel spray, the typical HVOF, which uses rather high SOD and a large particle, and the traditional APS, which lower standoff distance compared to HVOF. So this gives us a quick comparison of what we should do when we are trying to spray a smaller particle in a suspension. We should go closer, and we are able to use particles down the nanometer, 50 nanometer range. Thank you. Hi there. This will be the final map that we'll present in the interest of time, and this is a sliding speed versus normalized wear rate against a steel counterbody. Here we can see that there's probably around 100 to 150 points, but we can't really see the points here due to them being spaced out in here. So the advantage of having the ability to change this to log can be seen here. Now they are all spaced out, and this is done with various thermospray coatings being in sliding motion against a hardened steel counterbody, which is around 60 HRC in hardness. We can see here the normalized wear rate, the units are given here, versus the sliding speed. Depending on the material, you can see that they have various wear rate. This is a very useful tool for engineers who want to have a quick material selection procedure for a particular application whereby the coating is sliding against something hard. Let's go to coating material class. We can see that most of them are ceramics. The ceramics normally have able to take a higher speed with various different wear rates. The composites have a range of them, whereas your metals are towards the lower end for wear applications. If we go down to the spray type, we can see that mainly for wear application is by air plasma spray. Arc spray has a few points in there. Cold spray, which is up and coming, has a few points, and so on and so forth. Let's go back to coating material class. Say if I'm interested in this point again, I can look at the normalized wear rate, then I know that the sliding speed is 0.5 meters per second. And the paper can be seen here, reported in 2000. So thank you for watching the MONA program demonstration. If you have any questions, please feel free to contact me or Professor Bernd, and I hope you enjoyed watching this program as much as I enjoyed presenting it to you. Thank you and goodbye.